Good day. Welcome to the 8th lecture of metal forming. In this lecture, I am going to explain the different defects associated with the rolling process. So in the last class, we discussed different types of forces or the rolling forces required for plastic deformation of the material. And here, during this rolling process, there are different defects may be developed on the workpiece, or maybe some deflection like phenomena may also occur in the roller. So here in this lecture, I am going to explain different defects associated with the rolling process. In this rolling process, basically there are two elastic deformation may occur on the roller because of the rolling force. So in the last class, we discussed about the rolling force. When we apply, consider two roller. Okay, this is two roller, and I kept a workpiece in between these two roller. So this is my workpiece. So when I start to deform this workpiece, there will be a roll force, reaction roll force will be developed from the workpiece to roller. Okay, so some reaction roll force will be developed, and this reaction roll force may cause deflection on the roller. A elastic deflection or elastic deformation may be developed in the roller itself. Even we make the roller with a high hardness material like a forged steel, etc. But even under this rolling force, there may be a chance for the elastic deformation. So this elastic deformation is the reason for roll deflection and roll flattening. So here these are the two causes of defects in the rolling process. One of the main causes of the defects in the rolling process. So what is roll deflection? When these rollers, two rollers are rotating in a flat rolling cases, these two rollers are rotating, and we supply a workpiece, and when the workpiece is passing through the gap between the rollers, its thickness is reduced. So during this deformation process, some amount of reaction forces will be act on the roller itself. Okay, so these reaction forces try to deflect the rollers, or initially the rollers are in this condition, but when these reaction forces are acting on the rollers, what happens? The rollers try to deflect like this. It starts to bend like this. Okay, so that is the reason for roller deflection. So because of the forces acting on the rollers undergoes the changes in the shape during the rolling process. Just a straight beam deflect under transverse load. Okay, so for example, we can consider this roller as a straight beam. So when reaction forces are acting on this straight beam, what happens? The beam starts to deflect or beam starts to bend. Similarly, in this case, the roller also starts to bend. So here we can see this is the roller, and when this upward reaction force or downward reaction force develop, what happens? Starts to bend like this. Okay, so during the plastic deformation stage, this will be the condition of the roller. It is not straight, it is a bent structure or a deflected shape we can see on the roller. So this deflected shape of the roller is one of the reason for different types of defects. So, but this deflection is actually elastic deformation. This is an elastic deformation. After the removal of, after rolling process, the roller come back to its initial shape and size. But this elastic deformation change the gap or change the straightness of the roller. Thereby, it also affect the final deformation of the workpiece. So this is a elastic deformation. So as expected, higher the elastic modulus of the roller, then the deflection will be smaller. If the E value is very high, then there is no chance for bending, because we know the bending EI, the flexural rigidity, If E value is high, then the flexure rigidity also high. There is a chance of bending is lower in case of higher elastic modulus material. And the roll force tends to bend the rollers, resulting in a strip that is thicker at its center than its edges. So when we roll a workpiece using these deflector rollers, what happened? The final product will be like this. Final product actually, for example, this is my initial workpiece. This is my initial workpiece, and after rolling, the final product may be like this. Final product may be like this. We can see this is not rectangle. Actually, if the rollers are straight, then we get a final product which is perfectly rectangular in cross section. But due to this deflection of the roller, the final product will be like this. The cross section of the final product is like this. Okay. So here we can see the final strip that is thicker at the center. We can see the thickness here. It is thicker at the center than the edges. So during the plastic deformation, since we can see the profile here, after deflection of the roller, see the profile of or the gap area between the roller. So this is the profile. So when material deform plastically through this gap, the final material also will have this type of profile. This type of profile. So that is this type of profile is one defect in a rolling process. So what is the remedy for this? How can we avoid this? We cannot avoid deflection because every material will have some amount of deflection. Or one choice is that, or one remedy is that we can use a material that has very high flexure rigidity, or that has very high Young's modulus and very high I value or moment of inertia. Then we can say the bending or the deflection can be comparatively low. So that is the one remedy to avoid this problem. And second one is that avoid this problem, grind the roll in such a way that the diameter at the center is slightly larger than at the edges. This is known as camber. So this is the second remedy to avoid the deformation like this. What we do, for example, here, this is a very straight roll. We can see this is a very straight roll, and this is the initial thickness of the workpiece. Okay. After the rolling process, what happened? The roller is deflected like this. See this? We can see a curve here. So the roller is deflected like this, and the final product also will be this is not a perfectly rectangle. We can see a crown shaped final product is the output from this roller. So this is not a perfect rolling process. So what we can do, first method is increase EI value, flexure rigidity of the material, use a material with a high flexure rigidity, then we can avoid this type of deflection. So we can produce a product with a perfect flatness. Our second remedy is that instead of using a straight roller, we are not using a straight roller. Instead of that, we grind the one portion of the roller. So this will be the shape of the roller which we use to avoid this roller deflection. So when we use this type of roller, this is called camber. The curvature is known as camber. So this is called camber roller. Okay. So what is the advantage of using this type of roller? when we use this type of roller, we can see a camber here. So a curvature, a convex shape curvature we can see on this camber, on this roller. And when we do a rolling process on this rectangular workpiece using a camber roller, what happened? After the deflection of the roller, this actually initially it was like this. Initially the roller was like this, but after deflection, this convex profile changes to straight profile. Okay, so we provide a positive deflection or positive amount of material on the roller, that is called camber, a convex profile on the roller. So this convex profile when deflected gives a straight profile. We got a straight profile. So this is called camber. So we can see another figure. So this is a first case. We use a straight roller here. So when we do a rolling operation with a straight roller, we can see the output product. After deflection, we got an output product with a curve at the top. We can see a curve at this top. Okay, so the output product will not be a perfectly rectangle or not a perfectly flat output product. Okay, so what we do, the remedy is that instead of using this straight roller, we use a roller with a camber. So here we can see some convex profile on this roller. So after deflection, what happened? After deflection of this roller, we can see this. After deflection, this area, that means in the rolling gap area where the under this force, the roller is deflected and it turns to straight. This curved profile is changed to straight. So we can provide a camber to avoid this type of roller deflection. So the output product will be a rectangular product. See this, a flat product. So that is the first case, roller deflection. And the roller deflection, to reduce the effect of deflection, the rod also can be subjected to external bending. So that is the another third remedy. So when a force is applied on this roller, it starts to deflect like this. Okay, to avoid this deflection, this type of deflection, what we do, in the bearing area, we provide an opposite bending moment. Okay, so under the force, the roller starts to deflect like this. Under the rolling force, the roller starts to deflect like this. But we apply externally, we supply some amount of moment. Okay, this externally supplied moment turn the roller to a straight position. So that is another method to reduce the effect of deflection on the roller. And in hot rolling process, because of the heat generation, rolls can become slightly barreled. Okay, so due to heat generation, we can see this workpiece in the hot condition in case of hot rolling. So this area will be, there will be heat transfer from workpiece to this area. So that area starts to deform or starts to deflect, and we have to provide some camber, that is called thermal camber, to avoid this type of deflection on the roller under hot working condition. Okay, so this can be controlled by varying the location. Another method is, in case of hot rolling, vary the location of coolant on the rolling along their axial direction. When designed properly, such rollers produce flat strip. So this is the area where main heat transfer occur, okay, from the workpiece to roller. So provide a particular axial flow of coolant in this area so that we can maintain constant temperature throughout the roller. Thereby we can avoid this type of thermal camber on the roller. And this camber can be only correct for a certain load and width of the strip. So if the width of the strip is changed or the load is changed, correspondingly the deflection also will change, because the rolling force will be changed. Similarly, corresponding to that, this deflection, roll deflection also will change. So this particular camber only applicable for a certain load and strip of width of the strip. That is also important. So this is the first reason for the different defects in the rolling process, that is the roll deflection. So to avoid this roll deflection, we can provide camber as well as we can give external movements through the bearing onto this roller. And another method, use a material with a high Young's modulus and a high moment of inertia. So next one is the roll flattening. Roll flattening also an important phenomena that commonly we can see in this rolling process, that also produce a product with the defects. So what is roll flattening? In a vehicle tire, car tire, we can see this type of flattening of the tire. If the air pressure inside the tire is low, what happens in this area where from the surface, here in this area, a reaction force is developed from the surface into the tire. Okay, so in that area, in this area, we can see the curvature is not perfect. The tire curvature is not perfect, but instead of that, your actual profile is like this, but instead of that, the profile is, if the air pressure is low, the profile will be like this. Okay, so this area is a flat area. So this is actually the contact area between the tire and the surface, ground. So this will turns to a flat surface, the tire surface. We can see this in this image. This is a flat surface. Okay, this is a flat surface. So similar phenomena may also develop in the rolling process also. In the rolling process, we know the both the rollers are perfect, the surface is perfectly round, and this is the rolling process. We reduce the thickness in this rolling process. But if there may be a chance for the flattening of the rolls. So what happened when the rolls flattened? This will be the actual profile will be like this. But under roll force, the rollers starts to flatten. So here we can see. So this bottom region is actually a curvature profile. But when the roll force acting on this surface, what happened? The surface turns to flat, like this. Surface turns to flat. Okay, this surface is a flat surface. Similarly, in this region of the roller, this is a flat surface. So this roll flattening also a elastic deformation. After the removal of the rollers, workpiece, or after plastic deformation, the roller come back to its initial shape and size. So this is an elastic deformation. So this roll force also tends to flatten the rolls elastically, much like the flattening of the vehicle tires on the road. Flattening increases the roll radius, resulting in a larger contact area for same reduction in thickness. So what happened during roll flattening? See this in this figure. Actual roller is this one. This is actual roller. This is the actual roller. But when during the plastic deformation, the roll force develop on the rollers, and this roller starts to flatten. So this is the profile after flattened. This is the profile. Okay. So what happened to the radius of the roller? So this is initial before flattening, the roller radius is this much. this is R, this is the center of the roller. But after flattening, we can see this, the center has changed to this position, and we can see this is the radius. When we compare R and R dash, the R dash always greater than R. Okay, so the R dash will be greater than R. So the radius of the curvature increases. So this is the initial roller, and after flattening we can see R dash. So this radius of the curvature is increased after flattening. So how much it is increased? What is the relation between R dash and R? That is explained by this equation. It is called Hitchcock equation, and this is just for the reference. This R dash always will be greater than R. After flattening, the roller radius will increase. So actually the larger contact area, the roller radius increases, so the contact area will also increase for the same reduction thickness of the material, and that resulting in the increasing roller force. So the roller force will be increased, and because of the combined effect of flattening and the friction hill, reduction in thickness of the thin sheet is very difficult to obtain with the larger worked rollers. So the friction hill we already discussed. The friction will be maximum, or there is a friction increase from entry point to neutral point, then decrease from neutral point to exit point. That is called friction hill. And the combined effect of this flattening, roll flattening also increase the rolling force, because R value will increase, radius is increased, which increase the rolling force. So the friction hill and the rolling force, roll flattening, this combined effect actually is reduction in the thickness of the thin sheet will be very difficult. Under this circumstance, it will be very difficult to reduction in thickness of the thin sheet. And the usual solution is to roll with a workpiece using a backing rods. So use a backing rods to avoid this type of rod flattening. So that is the remedy for rod flattening. So this is another reason for the different defects in the rolling process. And third one is the spreading. Third, commonly we can see this phenomena in rolling process, that is spreading. So what is spreading? In case of when we analyze the rolling forces, flat rolling process, we have an assumption that the W0 equal to WF, that is width of the workpiece, that is W0, is equal to the width of the final product after rolling, that is WF. W0 and WF are same. That means there is no change in the width direction. There is no deformation in the width direction during the rolling process. And what is the reason for this? The reason is that when a roller, when the workpiece is passing through the roller, we can see in the width direction, this is the contact area in the width direction. Okay, the contact length or contact area in the width direction is very higher than that of the length direction or the thickness direction. In the length and thickness direction, we can see the contact area between the workpiece and the rollers is minimum. But in the in the width direction, we can see this is the width direction. This much of contact area is in between the roller and the workpiece. So when the contact area is very higher, then what is the reason? When the contact area is higher, then the friction also will be very higher in that direction. So in this direction, friction is very high in this direction. Since the contact area is very large in that direction, the friction also will be higher. So this friction offer a higher resistance to the flow of material in these two directions. In the width direction, the material flow is resisted by friction between the roller and the workpiece, and this friction is very higher value because of the higher contact area between this workpiece and the roller. So this is the reason for negligible deformation in the width direction. So we can assume there is no change in width during the flat rolling process. So W0 equal to WF. But this assumption is only valid when the width is very higher than that of the thickness of the workpiece. Okay, so this is width and this is the thickness. When width is much higher than that of the thickness, then only this assumption is valid. In some case, maybe for example, consider a workpiece like this. A workpiece like this. This is width and this is thickness. So in this case, the width is not much higher than that of the thickness. So in this case, the length of contact between the in the width direction as well as in the length or thickness direction is almost same. So there may be a chance for the deformation in the width direction. So material will deform in the width direction when this W by T is very less. So, but in rolling process, the deformation in the width direction we should avoid this deformation in the width direction. So, the deformation in this width direction is called a spreading. Spreading during rolling process. We can see during the rolling process, this is H0, this is HF. There is a reduction in thickness from H0 to HF. But when we take the top view, this is the top view of this rolling process. See this here, W0 is the initial width of the workpiece. But after rolling process, we can see there is a change in width from W0 to WF. So there is a width change. So this type of width change is called a spreading in rolling process. And where we can see this type of spreading, actually in plane strain condition, that means high width to thickness ratio. Here, when the width is very higher than that of the thickness, we cannot see or this spreading is very negligible. The deformation in the width direction is negligibly small. But when in case of square cross section, that means this type of profile cross section, this ratio is very small, W by T, or W is not much greater than T value. So in that case, there will be some spreading. There will be a deformation in the width direction. So this increase in width is called as spreading. In the calculation of the roll force, the width W is taken as average width. So in the previous derivations, when we calculate the pressure distribution or when we calculate the rolling force, we assume that there is no change in the thickness, or sorry, there is no change in the width dimension. We take W0 is equal to WF. But if there is any spreading, we have to consider that deformation in the width direction. So in that case, we cannot assume a plane strain deformation. It is not a plane strain deformation. So in that case, we take the average width for the calculation. In metal rolling process, the plastic deformation causes a reduction in thickness, will also cause increase in width of the part, and this is called spreading. So what are the reasons? Spreading increase with the decrease in the width to thickness ratio. If you take a workpiece with a square cross section, width is almost same as that of thickness, then there is a chance for the spreading of the during the plastic deformation. And the spreading also increase with the increase in friction value, decrease the ratio of the roll radius to strip thickness. Roll radius to strip thickness. This ratio decrease also a reason for the spreading phenomena in rolling process. And how can we prevent this spreading? So see this figure here, this is the initial thickness. After the rolling process, we can see the increase in the thickness, sorry, width. So initial width is this much, but after deformation, we can see there is an increase in this width value. So how can we prevent this deformation in the width direction? To prevent the deformation in the width direction, we can use additional rollers which is in the vertical axis. Additional rollers in the vertical axis can be used to avoid the deformation in the width direction. So this roller is actually in contact with the edges of the rolled product in the roll gap, thus provide a physical constraint to spreading. So here we can provide two vertical rollers. Two vertical rollers can be provided here, and this vertical rollers apply force in this direction. Apply force in this direction. So this will prevent a transverse or in the width direction, any plastic deformation in the width direction is prevented by this vertical rollers. So that thereby we can create a final product with the same width as that of the initial workpiece. So that is the best method to avoid spreading. Here we can see two edge rollers, and this edge rollers is actually prevent the deformation in the width direction. To prevent the deformation by applying a force in this direction. In this direction it apply force. Thereby we can avoid spreading process. So we can see another arrangement for reducing spreading.
Can be rolled down also
process we can see
during hot charging, thus saving energy and increasing throughput.
One member is moving. See this, one member is moving like this. You can see that.
Saving
this member, this is actually a component which is moving in this direction. Actually, this is an edge. We apply force through the edge of the workpiece, and this maintain a constant width. Even in the rolling process, there may be a chance for the increase in the width, but this compressive force, we apply compressive force in the width direction. So this compressive force actually reduce the or prevent the increase of width,
thus saving energy and increasing throughput.
Okay, so this is the spreading and preventive measures we can take to
be rolled
the spreading. So these are the three common phenomena we can see in the rolling process. The first one was roll deflection, second one was roll flattening, and third one is this spreading.
Can be
Next we will discuss the different rolling defects. Defects in rolling we can classify as a structural defects and surface defects. And surface defects actually is mainly because of the surface impurities, inclusions, etc. So there are different types of impurities and inclusions we can see on the surface. Actually in the previous video we can see
be rolled down
impurities.
Also during hot charging, thus saving.
See this, we can see some black color scales. See this black color scales. So actually in the hot rolling process, when this material come contact with the atmospheric oxygen and different gases, this hot material react with the atmospheric oxygen and form oxides, and these oxides actually stick on the surface of the workpiece, and this is actually an impurity, and which is one of the main reason for the surface defect. So during the rolling process we should remove all the scales is formed by using by high pressure water we can supply onto this workpiece to remove all the scales from the workpiece. So there are different methods to remove the scales. So this is the one of the reason, this impurities is the one of the reason for surface defect. So different inclusions, impurities, and diet scales, diet roll makers, etc. are the causes for the surface defects in the final rolled product. And another reason is the structural defects. Different structural impurities, etc., or structural inclusions, etc., is also a reason for the defects in the rolling process. And in hot rolling process, the distribution of temperature is the one factor which produce different types of defects. For example, this is a hot workpiece. In the hot workpiece, if there is any non-uniform flow of if the temperature is not uniform, okay, maybe in the edge region subjected to good conduction convection, so it this edge region may cool rapidly compared to this center region. Okay, so in the edge region maybe in a cold stage compared to the center region. So during the deformation, what happened? There will be a non-uniform plastic deformation across this width of the workpiece. because the edge regions are comparatively cold than that of the central region. Central region is hot because this edge region may conducted to, or the heat may be transferred to the atmosphere by conduction, convection, etc. Okay, so this difference in the temperature or distribution in the temperature may cause non-uniform plastic deformation during the rolling process, and this non-uniform plastic deformation causes cracks and tearings, etc. on the final rolled products. So we already discussed the flatness. So when we do rolling process, the camber we provide, if we are not providing any types of camber, the final product cross section will be like this. There will be a high thickness in this region and a low thickness in this region. Okay, in the edge area has a low thickness compared to center region. If we are not providing a camber on the roller, we using a straight roller. And if the camber is very high, okay, more than required, the camber which is provided on the roller is more than required, then what happens? The center region will be deformed higher than that of the edge region. So the final product will be like this. Okay, actual product required is of rectangular cross section, but if the camber allowance which is provided on the roller is very higher than that of the required one, then the final product cross section will be like this. If the camber is not provided as much as required, then the final product cross section will be like this. So this camber, the difference in camber, also a reason for different types of defects in the rolling process. So when the possible defect, when the rolling with the insufficient camber, that means actually we should provide a camber according to the deflection. We should provide a camber like this. This much amount of camber is required on the roller to produce a flat workpiece, flat output product, but we provide less camber. Okay, we are not provide this much, but the camber we provide is lesser than that of the required one. So when the camber is insufficient, then the final profile of the product will be like this. If the camber is insufficient, okay, there will be higher thickness in the output product at the center, but the edge regions, this is comparatively higher, subjected to higher plastic deformation. So this edge region will be, it has a lower thickness. So what is, when camber allowance is insufficient, actually the rolling force applied in the center region is comparatively low. That is the reason for higher thickness in the center region. But this camber provided on the edges, in the edge region, is plastically deformed higher than that of the center region. So this edge region subjected to compressive stress and the center region subjected to tensile stress. Okay, so here we can see severe deformation compared to the center region. So two edge regions subjected to severe deformation will develop a residual compressive stress, but in the center region that is not a heavily deformed, so that is only here tensile stress is developed. So this difference in stress developed on the final product may cause different types of defects. What are the different defects? The residual stress difference, we can see here the compressive residual stress is developed, but in the center region tensile residual stress is developed, and this difference in the compressive and tensile residual stress in the different regions of the final product may cause edge wrinkling, warping, center cranking, and residual stress distribution on the final product. So this insufficient camber is the reason for this type of defects. So the thicker center means the edge would plastically elongated more. The plastic deformation in the edge region is higher than that of the center region. So we can see a long edge in the longer edges in the final product. So here the center region is not deformed. The edge region is not comparatively higher deformation than that of the center region. So the chance for the elongation, here the deformation is higher in the edge region compared to center region. So in the edge region, the material elongated more than that of the center region. What happened? On the same material, same product, this region has more elongation than that of the center region. So what happened? There will be some wrinkling, a wave shape edges we can see on the output product. The reason is that the center region is plastically deformed more than that of the center region because of the insufficient camber. Okay, so that is the reason for edge wrinkling. Another one is wrapping. Actually, final product should be a perfectly flat final product, but after rolling we can see when we take the level difference based on the data, it is not a perfectly flat product. And in some case we can see the center cracks. Center cracks may be formed. And the center crack, the reason is that the residual stress in the center region is tensile residual stress. And this center tensile residual stress, this one, is the reason for center cracking. So we can see a molybdenum bar with a center cracking, the final product. So all these defects, the center cracking, wave edges, wrapping, residual stresses distribution, etc. are because of the insufficient camber. So when we provide a camber, the camber should be sufficient so that during the rolling process, the roller will be a straight, it will be a straight member, okay, by providing sufficient camber. So the wavy edges, the main reason is that this area is subjected to compressive residual stress, but in the center region subjected to tensile residual stress, and this also subjected to compressive residual stress. And this edge region is deformed, plastically deformed more than that of the center region. We can see in this figure. In this figure, it is clear. See this. Here the thickness is higher in the center region, but here the thickness is lower. That means the edge region is plastically deformed more than that of the center region. Okay. So what happened when the edge region is plastically deformed more? Where the length increase is higher than that of the center region. Okay. Here the change in length is higher than that of the center region. So this variation in the length of the same product is the reason for this type of wavy edges. So these edges, to compensate the increase in the length, the edges starts to fold and a wavy edges are formed. And second one is the over cambering. Over cambering. So in the previous figure, this is the over cambering. See this final product when we use a roller with the over cambering. What happened when the camber is when the roller is over cambered? This is the camber we provide on the roller. Okay, and after when the material passing through the rollers, the camber is not straight. Actually, in an ideal case, when the material passing through the roll gap, this by the deflection, the roller should convert into a straight one. Okay, but because of this over cambering, what happened? The roller will not be a straight one, but the roller shape is like this. Okay, it is not a perfectly straight. So what happened when material passing through this gap, resulting material will be like this. The center region, the plastic deformation, the center region will be higher than that of the edge region. See this, the edge region has lower thickness than that of the center region. Okay, so this is because of the over cambering. So this center region become thinner than that of the two edge regions. This is a thicker region. Okay, so this the severe deformation, plastic deformation will be developed in this region, and this region subjected to compressive force. So severe deformation region is subjected to compressive residual stress. But this two edge region, which is not severely deformed, okay, this is a thick region because of higher camber we provide. This two region is not severely deformed compared to the center region, and this two edge region is developed in that region develop a residual tensile stress. Okay, so this type of profile on the final product leads to different types of defects. So what are the defects? That is the center wrinkling and the splitting, edge cracking, residual stress. So already I discussed the residual stress. The center region will be severely deformed compared to the edge regions. So the center region is subjected to compressive residual stress, but in the edge region, which is subjected to tensile residual stress, there is a distribution of the residual stress across the final product. And here another one, this edge region. This edge region is subjected to tensile force. So this tensile force may create different cracks on the edges. Okay, so that is the reason for edge cracking. And another one is splitting. The center region, which is subject to very high compressive residual force, and this is a one reason for the splitting of the final product. Okay, the final product is split into two after rolling. Then center wrinkling. The center wrinkling, what is the reason for this? The center region, here we can see the center region is very thin than that of the two edge region. So the elongation or length change in the center region is higher than that of the edge region. This higher elongation in the center region may cause some wrinkling in the center region. But in the previous case, the wrinkling was in the edge regions because the edge region is severely deformed here. So the wrinkling is on the edge region, but here in this center region is subjected to severe deformation than that of the two edge regions. So the center region subjected to center wrinkling. So that is the four defects developed because of this over cambering of the rollers. And edging, we already discussed that the edge cracks are formed, and one defect is that the edging can also caused by inhomogeneous deformation in the thickness direction. For example, if the workpiece is subjected to light reduction. So this is my workpiece, for example, and I apply very small force in this workpiece through the rollers. Okay, so what happened when very small force is applied? Only this surface region is deformed. This surface region only deformed since the rolling force we applied is very small. So what happened in the surface region deform, and it is actually overhang into the outer region. So this is deformed and the surface region is overhang like this. Here also this is overhang compared to the center region. Okay, so see this, if only surface of the workpiece is deformed during the light reduction, the edges are concave. So when we take these edges, the edges will be like this. Okay, edges will be like this. So the final product will be like this. Okay, the edge region has more material on the surface compared to the center region. So a overhanging material we can see on the edges in the surface region. So is not compressed in subsequent steps of rolling, causing area under tensile stress leading to edge cracking. So this type of concave surface overhanging material is not compressed in subsequent steps. Okay, this overhanging material is not when it passing through the rolling gap, this overhanging material is not then compressed. Only we apply the force in this region. Okay, this overhanging material is not compressed further. So that is the reason for this. The residual tensile stress will be developed on this edge region, and this is the reason for this edge crack. Edge crack. Okay, the tensile stress is developed on this overhanging material, and these edges are cracks are produced and propagated. And with the heavy reduction, what happened when material is deformed with a large reduction? So this is my workpiece. When I do a heavy reduction, what happened? The deformation in the center region will be higher than that of the deformation in the center region will be higher than that of the these edge regions or the surface regions. Okay, so what happened? Final product will be like this. The center region will have more deformation. See this, the center region has more deformation than that of the two surface region. So that is the, we produce a barreled edges. The final product is not perfectly a flat edge, but it has a barreled edge. This is called barreled edge. This is because of the higher plastic deformation in the center region than that of the two surface region. And that is also a reason for the edge cracking. So heavy deformation as well as this light reduction is a reason for edge cracking, and the edge cracking is because of the tensile residual stress in the overhanging area of the final material when the deformation is a light reduction, and edge cracking is because of this overhanging, the barreled edges of the final material, final product. The compressive stress will be developed in this region, and this is the reason for this. Secondary tensile stress. Secondary tensile stress will be developed in this region, and that is the reason for the edge cracking. So this is the edge crack. We can see the edge crack here. And the center region we can see zipper cracks. So already here it is not mentioned. The center region actually subjected to compressive stress. Here we can see compressive residual stress is developed in the center region. Since the center region is heavily deformed, a thinner center region we can see, and this compressive residual stress and low ductility of the material. Another reason is low ductility of the material. A crack like this is formed. This is called zipper crack. It is like a zip in the center region. It's like a zip, and this is called zipper cracks formed on the final products after rolling. And another important defect which is formed, which we can commonly see in a rolled product is alligatoring. You know what is alligator? Same, this defect is almost similar to the mouth of the alligator. After rolling process, we can see such type of splitting of the roller from the center. So this is a very complex phenomena. This is because of inhomogeneous deformation. In the previous slide, we discussed the reason for the inhomogeneous deformation. During the light reduction, the surface area is subjected to deformation than that of the center region. But in case of heavy reduction, the center region is subjected to severe deformation than that of the surface region. So this difference in deformation or the distribution in the deformation is an inhomogeneous deformation. And this inhomogeneous deformation is the reason for alligatoring defects commonly we can see in the rolled product, which can be and this alligatoring will occur when the lateral spread is greater in the center than the surface. We already discussed that the barreling effect here. In the center region, the lateral spread in the center region is higher than that of the surface region. So this higher spreading in the center region is the one reason for this alligatoring defect. That is also a inhomogeneous deformation. So the surface will be in the tension, and so this surface area, the surface area will be in the tension, but the center region, this center region will be in compression. Okay, so what happened after rolling? The material like split like this from the center. Okay, so actually this some metallurgical weakness along the center line also accelerate this alligatoring defect. Here the work being rolled actually split into two during the process. Okay, after rolling, we can see this figure. This is my workpiece. After rolling, it is split into two in the center region, and one going in this direction, another going in this direction. It is actually like a mouth of alligator. So that is why it is called alligatoring. We can see the molybdenum rod and alligatoring defects after rolling on the molybdenum rod. So the center region is subjected to heavy compressive residual stress. Okay, this is subjected to compressive residual stress, and this compressive residual stress and the surface region subjected to tensile residual stress. Okay, so this inhomogeneous residual stress and some metallurgical weakness along the center line causes alligatoring defects in the rolled product. And we already discussed about the residual stress in the defects, the importance of the residual stress in the defects. Actually, when this residual stress actually because of the inhomogeneous plastic deformation. When we deform the material, uh, there will be a difference, a distribution in the deformation. Maybe in some case, if it is a heavy deformation, the center region will be deformed to large value than that of the surface region. For a light reduction of the rolling, the surface region is deformed than that of the center region. So there will be an inhomogeneous plastic deformation during rolling process, and this inhomogeneous deformation leads to residual stresses in the final product. And small diameter roller or small reduction in thickness tends to deform metal plastically at its surface. I already explained that when we do light reduction, the material only plastically deform in the surface region. The center region will be undeformed or lightly deformed. Okay, so the heavy deformation in the surface leads to high compressive residual stress on the surface. Okay, high compressive residual stress will be formed on the surface, and this is like a short pinning. What is short pinning? We introduce compressive residual stress on the material by short pinning. We actually throw small balls onto the surface with a very high velocity, and the impact of these small balls create a very compressive force on the surface. Thereby we can increase the compressive residual stress on the surface. That is called short pinning. And also burnishing is another process for increase the compressive residual stress, and this compressive residual stress is created with the rolling process. When we do light reduction, the surface is only deformed plastically, so that the center region subjected to compressive residual stress. Actually, this compressive residual stress is a good one, which increase the fatigue life, and we can reduce the or the life of the product can be increased by this compressive residual stress. But when we do a large deformation, when the deformation is large or heavy reduction of the product, what happens? The center region will be subjected to heavy deformation compared to the surface region, compared to this surface region. So center region is subjected to heavy deformation. So in this situation generate tensile residual stress on the surface. Okay, the center region subjected to in the center region we can see compressive residual stress. Okay, compressive residual stress, but in this here in the surface we can see tensile residual stress. Actually, this tensile residual stress is on the surface is not not good for a material with, which is applied in the fatigue area or cyclic load area, and this tensile residual stress on the surface is actually an agent for initiation of crack and the propagation of crack. So we should avoid the generation of tensile residual stress on the surface. So this is the distribution. You can see when we do a light reduction, the center, the red color one, that is only subjected to plastic deformation. The blue color one is not subjected to, the center region is not subjected to plastic deformation. So the center region will be under tension. We can see the center region will be under tension, but this surface region, the surface region will be under compression. Okay, so here we can see the surface region of the workpiece is under compression. You can see the compression, but the center region is subjected to tension residual stress. But during the heavy reduction, what happened? the material in the center region is only plastically deformed, but in the surface region, the plastic deformation is very minimum compared to the center region. So the center region will have higher compressive residual stress, but the surface region will have higher tensile residual stress. Okay, so there will be a distribution in the residual stress when the plastic deformation is not homogeneous, or inhomogeneous plastic deformation leads to this of difference in distribution of the residual stress. And during the deformation or during the rolling process, there may be a chance for the vibration and chatter. Okay, actually the vibration can be classified into two. One is forced vibration, and second one is self-excited vibration. Okay, these are the two types of vibration. Mainly in any machinery, we can see this type of two vibration. And the forced vibration is actually a periodic vibration. That is because of the misalignment of the different components in the machine, or maybe because of, during the working of the machine, maybe some mismatching like that, or unwanted force may be developed on the machine during this working. That is the reason for this forced vibration. And the forced vibration does not have any relation with the operation performed on the machine. Okay, this is actually because of these different misalignments, mismatch, and the different force developed in the machine. And second one is the self-excited vibration. And the self-excited vibration is because of the interaction between the machine and the rolling operation. So during the machining, or sorry, during the rolling process, there will be a dynamics for the structure. The machining member, the machine has a particular dynamics, and also there is a dynamics for the rolling operation. Okay, so this dynamics is actually the reason for this self-excited vibration. Okay, so there is a relation between the operation which is performed on the machine and the structural dynamics in case of self-excited vibration. But in case of forced vibration, different misalignments in the machine and the dynamics of the structure of the machine, etc., are the reason for this forced vibration. So this self-excited and forced vibration may cause different defects on the final product. So we should avoid this type of vibration by using damper, etc. And one important thing from this self-excited vibration is the chatter. The chatter may be produced. Chatter is the self-excited vibration, is defined as a self-excited vibration, and can occur in such metal forming and machining process as rolling, extrusion, drawing, machining, and grinding. So in every most of the manufacturing process, we can see this type of chatter type of self-excited vibration. So in rolling, this leads to periodic variation in thickness. What is the when there is any chatter during the rolling process, it leads to periodic variation in the thickness. Okay, the final product thickness will vary, and also the surface finish, it affects surface finish, and may lead to excessive scrap after rolling. So chatter in rolling can be found to occur predominantly in the tandem mill. Commonly we can see in the tandem mill this type of chatter. Chatter is a very complex phenomena. This is because of the structural dynamics of the mill and dynamics of the rolling operation. Rolling speed and lubrications are found to be two important characteristics which affect this chatter and vibration. So chatter can be reduced by increasing the distance between the strands of the rolling mills. So increase the distance between the two strands in the rolling mills, increase the strip width, decrease the reduction per pass. So do number of passes for a particular reduction, increase the roll radius, increase the strip roll friction, incorporating damper. So this damper can be in the support area when we incorporating a damper which absorb vibrations, we can avoid the chatter. So these are the different measures we can take to reduce the chatter. So that is about the vibration and chatter. So we should avoid this vibration and chatter to get a final rolled product, a defect-free final rolled product. Next one is the flat rolling process. We already discussed the flat rolling process and we analyzed the flat rolling process. We have two types of flat rolling, cold rolling and hot rolling. And this is the microstructure variation during the hot rolling process. Here initially we have, this is the ingot. After casting, we got this type of microstructure. And then during the rolling process, in a hot rolling process, the microstructure changes to coarse grain when we heat, and during the rolling process, these coarse grains changes to elongated grain after rolling, and then after recrystallization, this elongated grain converted to fine grained structure. So this is the change in the grain structure. I already explained this change in the grain structure during hot working process in the initial lectures of this metal forming. And we can do different, we can make different products using this rolling process. This is also I explained in the initial lectures. And this is also explained boom, slab, billets, etc. are the initial slab, billets, blooms, etc. are used for rolling operation. And this is classified based on the cross-section dimensions. That is also I explained in the initial lectures. And during the we can perform different rolling operations, different miscellaneous rolling operations are there, or flat rolling operations are there, and we can make different components by performing rolling operations. We can make seamless pipes, different structural components, and plates, etc. by a rolling process. And during the rolling process, we do pickling with acid. This is actually surface treatments on the rolled product. And during the rolling process, we do scraping. We remove the scales from the workpiece. These scales may cause different surface defects during the for the final product. So we have to remove. We should remove the scales during the rolling process. For that, we can use a torch, and or we can we can supply high pressure water to the workpiece to remove the scales. So next I will show a video how we perform different rolling operation.
After pre-rolling of
The initial ingot we produce for the rolling operation is by continuous casting process. So this is a continuous casting process.
continuous cast material or ingots in the blooming mill, billets are transported to a heating furnace to be reheated to the correct rolling temperature.
And we produce billets from the cast. So this is
the billets are then rolled in Sandvik's modern rolling mill, where round and square billets are rolled to a wide variety of sizes. The new mill provides quick product dimension changeover, short lead times, energy savings and excellent product quality. The mill is integrated with the blooming mill to form one continuous production line.
So we use the same roller for
billets and bars are rolled to finished size in 1 to 6 passes.
So this is the removal of scales. We can see scales. This is a very hot workpiece. So the atmospheric oxygen and other gases react with the hot workpiece and produce scales on the surface. And we should remove the scales by, we can use different methods. Here a high pressure water is used to remove the scales. So during the rolling process, we should remove the scales. So through the conveyor, it enters the roller. So the rectangular workpiece is converted to round bar. Again, its diameter is reduced.
Cut into requested lengths. The bars are inspected before dispatch or put through further internal processing. Full traceability is maintained throughout the manufacturing process. Before the bar steel is used for tube manufacturing, its chemical composition
is actually an extrusion process for producing seamless pipes, and we can use either extrusion or management process. In the next lecture, I will explain what is management or rotary tube piercing process to produce seamless pipes. So I skip this area because in this video the extrusion process is used to produce hollow pipes. So that I skip this area. So this is using management process. This is an extrusion process. similar to the extrusion process, we can use Mannesmann or
Processing.
rotary tube piercing process to produce hollow pipes.
Working according to customer
So see this,
specifications
we
or
got
used
finally we
as the
got a
starting
hollow
point
workpiece,
for further processing.
hollow product. Then we do different treatments, pickling, different surface treatments we can do on this. Then
The
this is very
extruded
important
tubes are
process
rapidly
during the rolling process. This is called leveling. So this is a set of leveling rollers we use to actually after rolling, the final product may not be straight. Okay, so there will be some bending on the final product. To increase the straightness of the final product, we use leveling. So here we use leveling rollers.
straightened and pickled in acid
So
to
we
remove
straighten.
glass
This
and
is
metal
pickling.
oxides. After deburring,
This is the pickling. So after leveling,
the extruded tubes are rapidly straightened and pickled in acid to remove glass and metal oxides. After deburring, dimensional checking
and inspection, the tubes are ready for final production.
After pickling, we got the
Following
final
visual inspection and X-ray
Then we
spectrometry
do different
to
types of NDT test on this material. So this is again leveled and grind polished. Then we do different NDT tests. You already studied different types of non-destructive testing. Then after non-destructive testing, we got the final product. So we can check the
ensure the material
microsector.
meets custom. Tubes are stored, collected,
Then after to the logistics. Okay, so in plate mill, hot rolling, continuous milling, and cold rolling, we can use different pickling setup. Here in this plate milling, first initially we heat the material, then we do rough milling. So there will be a large reduction during the rough milling or rough rolling. Then we do finished rolling. In that case of finished rolling, the amount of reduction is very minimum. Then we do cooling. It may be a quenching. Then after quenching, we got plates with a higher strength. Then in hot rolling process, again we do rough rolling, then finished rolling. Then after finished rolling, we do forced cooling. Forced cooling is similar to the quenching. Then we cooled final product we got after continuous cold rolling. Then cold rolling process, we have a strip unwind from the coiler. Then we do pickling to remove the oxides, etc. Then we do cold rolling. Okay, so these are the different varieties of rolling process. And in rolling, one variety is packed rolling. In packed rolling, the mainly we already discussed about in the analysis area, when the reduction thickness is very low or initial workpiece thickness is very low, then the amount of rolling force required is very huge, okay, for the deformation or for the reduction. So for the thin sheets or foils, making by rolling process is very difficult. So in that case, we use packed rolling. Packed rolling is nothing but it is a flat rolling process. But for example, in case of making of aluminum foils, you may see these aluminum foil sheets. To make this aluminum foil sheet, we know the thickness of the aluminum foil sheet is very low. Okay, so for rolling of this type of aluminum foil sheets, what we do is that we use packed rolling. Okay, so we cannot use a single sheet for rolling. So when we use a single sheet for rolling, we need very high amount of rolling force, and there may be a chance for the defects of the final products if you use a single sheet. So in that case, we use a packed rolling. For that, we use this method. We make a pack of number of such foils. Okay, this we arrange such type of a package of number of such foils, very thin sheets, and we roll the entire package. Okay, so this is the roll input we fed through this gap. Okay, so actually a layers of the material is actually fed through this gap. So then we do rolling process, and after rolling we can take each foil separately, that is packed rolling. So we need to provide lubrication in between the rollers, then only we can avoid the sticking or atomic bonding between the sheets. Okay, so this packed rolling is a flat rolling operation in which 2 or more layers of metals are rolled together. Okay, so we arrange like a different layers, and we rolled together. The entire pack is rolled together. That is called a pack rolling. So the several thin film sheets can be produced at a same time by this process, and it has a very several advantages, including not requiring a usual small roller size due to the increase in static thickness of the pack of roll stock. So if we use a single sheet, then we need a very small size rollers. Okay, but if we use this type of layers one by together, then we can use a higher size rollers. This allows the use of conventional rolling equipment. So by using this pack rolling, we can use this conventional rolling, or conventional rollers can be used for pack rolling. But if you use a single sheet for rolling, then we need separate arrangement for rolling, and the productivity also will be low if you use a single sheet. So by this method we can produce aluminum foils, and which can be used for lithographic printing, food packaging, and electronic industries, etc. We can use this aluminum foils. The next one is temper rolling or skin pass. So during the rolling process or in the plastic deformation, as you know, in the stress strain diagram, for a low carbon steel, there will be upper yield point, then a lower yield point. We have a uniform elongation or plastic elongation area. Then we have a strain hardened area. So this is the elongation area, uniform elongation area. In this area, actually there are some metallurgical phenomena may occur, and some Lude's band is produced on the material. So when we do plastic deformation, a band is formed at the starting point, and this band is propagated in this direction, and this band during the plastic deformation disappear at this end. Okay, and this Lude's band is formed because of the pinning of the dislocations during the plastic deformation, and this we should avoid this Lude's band, because this Lude's band produce stretching and stretching of some stretch marks on the final product. So we should avoid this Lude's band formation. For that, we use light pass of 0.5 to 1.5 reduction called a temper rolling or skin rolling. We use very light reduction, that is 0.5 to 1.5 percentage reduction, and in the final stage, that is called temper rolling. And this temper rolling can actually remedy to avoid this Lude's band, or to avoid these stretcher strains. Stretcher marks can be seen on the surface of the final product. So to avoid that, we can use this skin pass or temper rolling. So I already explained the importance of levering rollers. So after rolling operations, after completing the rolling operations, the final product may not be a straight product. Okay, the final product may have some bending. Okay, for example, if you make a seamless pipe, the seamless pipe is not a perfectly straight. There will be some bending, and to convert this bent pipe into a straight pipe, we use this levering rollers. So in the last video, we have seen this type of levering rollers. So when this final product is passing through the levering rollers, we got a straight final product. Okay, so straightening unit. This is a straightening unit. So that is the importance of leveling rollers. We use these leveling rollers in the end of the rolling process to increase the straightness of the final product. So we already discussed different types of mills used. This is one pass, 2 high reverse, 3 high mill, 4 high mill, and a cluster mill, etc. We already discussed. So this type of mills can be used in the rolling operation. So next we will see a rolling operation. What we studied in these lectures can be seen in this video. So this is the final product rolled or coiled. The initial billet, final product. So this is the different process involved in the rolling. So for hot rolling, initially we have a heating furnace. This is a heating furnace. So it is after heating, the raw material passing through the conveyor into the descaling unit. I already explained what is the importance of scaling. Some impurities, oxides may be formed on the surface of the hot workpiece. So we should remove these oxides before rolling in order to avoid any surface defects during the rolling. So that we use a descaling unit here. High pressure water can be supplied to remove the scales or oxides. So this is the roughing mill. Higher reduction actually, larger reduction is actually applied on the workpiece in the roughing mill. So this is a reversing stand. There will be a forward and a reverse motion. There are a number of passes may be applied for the total reduction of the workpiece in the roughing mill. That this is the intermediate stand. This is the measuring station. Measure the variation in the draft and width, etc. With cooling. So by this cooling, we can make a different microstructure. So depending upon the microstructure requirement, we can do strip cooling. Then after strip cooling, the next one is the edge heater. So I already explained. During the transportation through the conveyor, these edges is in contact with the atmosphere, have more conduction of heat compared to the center region. So the center region will be in the hot condition, but the edge region will be in the cold condition. So this difference in temperature in this workpiece may cause different distribution of stresses. The different residual stress may be developed because of this distribution of the temperature in the workpiece. To avoid that, we heat intermediately, we heat the edges of the workpiece so that the temperature throughout the workpiece will be uniform. After edge heater, we shear some portion from the edges to clean the edges. Then again we do descaling. Depending upon the process, it may vary. Then this is the finishing drive. So initially we do rough rolling. Then after this scaling, descaling, etc., we do the finishing rolling. So here we use a series of rollers, and we here in the reduction will be very small in the finishing rolling. Different heat treatments, surface heat treatments, pickling, etc. So this is a cooling station. Actually, according to the microstructure requirements, etc., we cool the final product. Then we measure using a measuring system. Then we coiled.
Before the slab can be processed, it must be...
So this animation, here this is the actual working.
heated. The slab is continuously cast and has the dimensions required for the final product of a correct weight, width, and thickness.
In the furnace.
These furnaces heat the material to about 1200 degrees centigrade. Two walking beam furnaces feed the material through the oven.
1200 degrees Celsius.
The heating is especially important as it affects the properties of the material. If the material is not sufficiently heated, incorrect material properties will arise. This is due to carbides and nitrates failing to dissolve.
So we can see scales on the
During the
bottom.
heating process and the transport to the roughing mill, the hot material reacts to the oxygen in the air, and a mill scale consisting of oxide is formed on the surface. If the oxide layer remains on the material during rolling, the layer risks being rolled into the steel material, adversely affecting the surface quality of the final product. The material must undergo a mill scale cleansing before rolling. In order to cleanse the surface, water is sprayed at high pressure, 160 bar.
So this is the descaling process. After rough rolling, we do descaling to remove the scales, oxides, etc. from the surface. High pressure water is applied to remove the scales.
After the material has undergone a surface cleansing, it's sent to the roughing mill. Here the material is rolled from its original
After
thickness
descaling, we go to the workpiece is moving to roughing mill, okay, where we do larger reduction.
of 22 centimeters down to about 3 centimeters.
So here in this case,
This is a very significant reduction.
4 high mill is used.
At this roughing mill, a powerful 4-high rolling mill is used. That is, 2 backup rolls and 2 smaller working rolls. The backup rolls are often cast steel rolls. The working rolls must have very smooth surfaces and tolerate high temperatures and wear, as they are in direct contact with the material.
So we need to 3 centimeter reduction during the roughing.
This particular material is rolled with 5 passes, where 1 pass means that the material passes through the rolls once.
After roughing.
The material is surface cleansed several times during the roughing mill process to remove any new traces of mill scale. In order to control the width of the material, vertical rolls are used.
Vertical rollers are used to control the width. So this is the product after
The material
roughing mill.
is now called transfer bars. After the roughing mill, the transfer bar is rolled up in a coil box.
So after roughing mill, in this case, it is called this coiling is actually helps to transport this roughed product into the finishing area. So for easy transportation, this roughed product is rough milled products or rough rolled product is coiled. In some case, this type of coiling may not see after rough rolling. It is directly passed to the finished rolling. So up to this point, we do heating of the workpiece, then we do rough milling or rough rolling, then we do scaling, descaling.
Coil box's primary purpose is to save space, but when inside the coil box, a temperature equalization also occurs. The temperature difference between the ends of the material is minimized as the transfer bar is coiled together. When the transfer bar is removed from the coil box, it has a temperature of about 1050 degrees centigrade. The ends of the transfer bar are cut off and the bar undergoes further mill scale removal. After this, it's time for the next stage, the finishing mill.
This is the setup used for finishing rolling, finished rolling.
This mill consists of 6 stands in the shape of 4 high rolling mills. Here, the transfer
So 6 strands with the 4 high rolling mills is used for finished rolling.
bars, now called strips, are rolled into a thickness of between 16 and 1.8 millimeters.
So
Between
here
the
is finishing 3 mm to 1.6 millimeter reduction, but in the rough rolling 25 to 3 mm. So huge reduction in the rough rolling, but in the finished rolling only reduced from 3 mm to 1.6 mm.
Rolls, we see an up looper, which measures and controls, amongst other things, the line speed and the strip tension. The swinging motion that can be observed is when the up looper is adjusting itself. In order to control the profile and the flatness of the strips, the working rolls are horizontally adjustable. The first stands control the profile, and in the later stands the flatness is controlled. It's very important to have a correct strip profile and flatness before any post-processing starts.
After the finished
The cooling rate is adapted to each
heat
strip.
treatment process. Then after heat treatment process, we can coil like this. This is the final product after rolling.
To produce the appropriate microstructure and material properties of the end product. When the strip is passed through the cooling section, it's coiled in. The temperature during coiling varies between 150 and 750 degrees centigrade, depending on the properties assigned to the material. After coiling and the subsequent cooling, the strip can be sold directly to the customer or undergo additional processing stages.
Final product after the rolling process.
For instance, cold rolling.
Of the intermediate stage. The rolling process is computer controlled. Okay, so here we can see this is the final product.
Coiling and the subsequent
1.6 mm. 1.6 mm very small strips are produced, and this is the initial workpiece. You can see the initial workpiece. This one is the initial workpiece. See this thickness, it has a 25 mm thickness. So the 25 mm thickness workpiece is converted to 1.3 mm thickness final product. Okay, so that is input and output workpiece and output product from the rolling process. So that is about rolling. So after this, I concluding this lecture. Thank you.